Math 265A, Quest to College. I'm Joe Vasta, and this is Review 5, our last review for the class. So let's work on some problems. So what do we have here? We have the velocity function. Here's a time interval, and they're asking us to do a few things. They're saying find the displacement, find the average velocity, find the total distance traveled, and then find all times that satisfy the mean value theorem, 2 decimal places. So, how do I find the displacement? Well, this is something hopefully we have remembered about this class, that the displacement from -2 to 0 happens to be the definite integral from -2 to 0 of the velocity function. So this is 3t squared minus 6t minus 9 dt. So that is the displacement when you integrate over the time interval of the instantaneous velocity. Hopefully that's something that's stuck with you in your head. Okay, so I'm going to go ahead and integrate this. I get t cubed minus, this is going to be minus 6t squared over 2, so this is going to be minus 3t squared minus 9t. Now remember, I don't have to put the plus c on a definite integral, because what I'm going to be doing is evaluating this thing from -2 to 0. This right here is the position function. It's one of the position functions, and remember, we go s of 0 minus s of -2. That's kind of what we're doing here. So let's go ahead and plug 0 in there. When I plug 0 in there, I get 0 minus 0 minus 0. Here's the fundamental theorem of calculus, where you go minus, and then we put the -2 in there. So when I do that, I get -8, because that's -2 times -2 times -2. Then we have minus 3 times -2 squared. So -2 squared is 4. 4 times -3 is -12. And then this one's going to give me -9 times -2, which is plus 18. Wow, so that's 0. This is negative. And then in here we have a -20 plus 18, which gives you a -2. And looks like the displacement of the bug on the number line, given this velocity function, is 2 feet. If you're thinking about that number line, you can say, well, that's 2 feet to the right that he's displaced within that time interval. The average velocity, well, the average velocity over the time interval is really the average value of that function. And the average value of that function, well, I mean, the first way we learned this is really it's just the displacement over the time. You know, when we first learned it, we went s of 0 minus s of -2 divided by 0 minus -2. And that's exactly what we're doing when I say it's the average value of the function. It's 1 over 0 minus a -2 times this. This is the new way of saying average value of a function, but it's the average velocity. Let me write this down. Not that you would write this all down if you were given a problem like this. But this guy right here, I mean, we already know. That's what we did in the last part right there, part B. So let me just label this. This is A. This is B. And so what do we have here? We have really just 1/2. I mean, that is something divided by the time of 2. And 1/2 times 2 in sense calculation is 1. Velocity, so this is going to be feet per second. Now, if I gave a problem like this on the exam, I would spell out a few more things, because the way I wrote it, I didn't tell you what the measurement was, feet, and I didn't tell you the time, was seconds. But with the bug handouts, I've always done feet and seconds. On the test, I would clarify this. I would give more instruction. Part C is what we are going to do now. We want to find the total distance traveled on the time interval. So let's go ahead and do this. Another piece of paper. Part C is total distance traveled on this time interval from -2 to 0. Now, before we find the total distance traveled, I'd like to find the rest times, if there are any rest times within our interval. And so to find the rest times, I take the velocity function and set it equal to 0. Now my velocity function, which is a bit out of range on this, well, there it is right there. It is 3t squared minus 6t minus 9. This is going to be set equal to 0, and this is going to find out where the velocity is 0. That's really what we mean by rest times. So I'm going to divide everything in that equation by 3. I have t squared minus 2t minus 3 equals 0. Factors of 3 that subtracting give me 2 would be 3 and 1, so this thing can factor, and I'm going to get a -2 in the middle. So here's t, here's 3 and 1. The negative has to be there, and the positive has to be there. And so those give me 2 t values. T equals 3, and t equals -1. Okay, so do any of these values fall in this interval from -2 to 0? And yes, this one does right here. T equals -1. So what am I going to do about that? What I'm going to do about that is the following. I have to break my interval up to find the total distance traveled. The total distance traveled is integral from -2, that's 2 seconds ago, up to -1 of the velocity dt. Now, I put absolute values around the velocity, which is correct, but we could, if we want, put the absolute value there. And then I'm going to go ahead and figure out so this is really the net area from -2 to -1, and then I'm going to go from -1 to 0 of the velocity function, find its net area, and take the absolute value. So this might remind you of when we did this, when we said it's really the displacement from -2 to -1, then we did the absolute value, plus, this is what we did before we learned integration, displacement, and with the rest times being in the middle from -1 to 0. Absolute value. That's exactly what we're doing here. So what we really need to do is we've already integrated v of t, and that integration of v of t is out of range, but when we did it, you can look back on this. This was t cubed minus 3t squared minus 9t. And so this one gets evaluated from -2 to -1, and then we have the same thing over here, which is t cubed minus 3t squared minus 9t gets evaluated from -1 to 0. And don't forget, and some of you probably thought I was going to forget this, the absolute values. Okay, now I think, well, now it's just plugging numbers into the function. I believe when we plugged, well, we haven't plugged -1 in, so when I plug -1 in there, I'm going to get, let's just do that over here, t cubed minus 3t squared minus 9t. When I plug a -1 in there, I'm going to get -1 minus 3 plus 9. So I'm going to get 9 minus 4, which is 5. So -1 gets plugged in there, I get 5. -2 gets plugged in there. We already did that on the above calculation. I believe when I did that, so this is 5 minus, we plugged -2 in there, we ended up getting -2. Okay, so this is the absolute value of that, which really, I mean, we'll still put it. And then over here, when I put 0 into this, I get 0. I'll put that in there. Minus, and putting a -1 in there will give me a 5. There's the absolute value of that. Okay, so I'm running out of room here. So this gives me 5 plus 2, which is 7. Absolute value of 7 is 7. This gives me a -5. The absolute value of -5 is 5. 7 plus 5 is 12. The bug's total distance traveled from -2 to 0 was 12 feet. Let's continue, because I think there was one more problem. It said, find all the times, so here it is right here. Find all the times that satisfy the mean value theorem, or the conclusion of the mean value theorem, and we're going to round to 2 decimal places. Now, the conclusion of the mean value theorem says there is a time within the time interval where the velocity, so there's a time in there that has a velocity that equals the average velocity. Okay, so we need a new piece of paper here. And so what does this mean? Well, we have the average velocity. We compute it was -2 to 0. It was 1 feet per second. And here is the velocity function that was given to us. V of t equals 3t squared minus 6t minus 9. Okay, so this is the instantaneous velocity at any point, any time value. And this is the average velocity within this time interval. Well, what the mean value theorem says is there's a time between -2 and 0 where this will have a value of 1. So what you do to find the times that satisfy the conclusion of the mean value theorem is set this velocity function equal to 1 to find out what time that would be at. And so that's what I'm going to do. I'm going to go 3t squared minus 6t minus 9 equals 1. And also when you do this, maybe you want to hope that you don't have to use the quadratic formula. So this is 3t, I just jinxed it, didn't I? 3t squared minus 6t minus 10 equals 0. 3 times 10 is 30. Factors of 30 that subtracting give you 6. 1 and 30, 2 and 15, 3 and 10. Almost. That gives you 7 when you subtract. 4, 5, and 6. Okay, so no. It's not going to factor, so we're going to do the quadratic formula. The quadratic formula says -b plus or minus the square root of b squared, so this is 36, minus 4 times a times c. So there's a negative there, so this is going to really be plus 120. This is all over 2a. So 2 times 3, 6. So our quadratic formula gives us 6 plus or minus the square root of 156 all over 6. Now, because they told me to round to 2 decimal places, I'm going to go ahead and enter that into my calculator. So I have 6 plus the square root of 156 divided by 6, and I'm getting 3.0 1.08. And then I'm going to go ahead and put the minus in there in my calculator, and I'm getting negative 1.08. So lots of times you say, well, when you have two of them and one's a negative, we cross the negative out. But what? So we've just found a time. So this is t equals. But which time falls within our time interval? And that time is not 3.08. That's the one we get rid of because it's not in our time interval. The time that falls in there happens to be negative 1.08 seconds. And so we have now found a time within the time interval where the instantaneous velocity, so this guy has instantaneous velocity 1, or approximately 1, which equals the average velocity in the time interval. And we can say things about the slope of a tangent and the slope of the secant, but we're really not looking at this problem from that angle. But that could all be said. I think we'll label this D, and that's the end of this problem. So this was bug 13, problem number 13, which took 3 pieces of paper. Let's move on to our next problem. Okay, so 4.9 is what we'll do a few problems on. And 4.9, I went ahead and picked number 38, which looks like this. Wow. So they want us to find the antiderivative of this. And before you do a U substitution, let's go ahead and factor the top. Okay, so I'm going to go off to the side and write y cubed minus 9y squared plus 20y. Now, it might not factor. Let's see what happens. I'll factor a y out. So I have y times y squared minus 9y plus 20. Are there factors of 20 that add up to give you 9? And the answer is yes, 4 and 5. So I'm going to write 4 here and a 5 there, and I want my 9 to be negative, so I'm going to put negatives on both of them. So it just so happens that the top can factor into y minus 4, y minus 5, all over y minus 4. So look what happens here. The y minus 4's cancel. So we did some algebra to the integrand, which is good. And I have the integral of y times y minus 5. This is dy. Okay, so now to find the antiderivative, I should probably actually multiply the y back through. So this gives me y squared minus 5y dy. Now it's time to take out your antiderivative gun and fire away at this. This one's going to be y cubed over 3, using the power rule of antidifferentiation. And then this one's going to be minus 5 y squared over 2. And then don't forget, plus c. It's kind of funny that I could have actually put the answer here. I don't know what I was thinking. I guess I panicked. That is the answer to problem number 38. I picked some even ones, you know, because maybe you didn't do the even problems. I assigned odds mostly. Let's go ahead and do another problem from 4.9, which is this messy problem right here. Wow. So I think the same thing's going to happen. I think we're going to do some algebra on this, maybe some trig. We'll see what happens, and try to simplify that integrand. So I'm going to factor out a secant squared on the top. So secant squared v, okay, that's kind of annoying to have that because we're used to writing x's. Then we have a secant v minus 1. This is all over secant v minus 1. Sad. Okay, good thing I wasn't doing secant x. That would have been quite embarrassing there. Okay, notice that when you have secant cubed, it's really the secant v in parentheses cubed. So that's why you're able to get away with this. And look what we have. We have some canceling that can happen. So this gives us the integral of the secant squared v dv. Now, this one should be memorized. You know, these are good things to memorize because you're going to be taking another calculus class most likely. And the antiderivative of secant squared is the tangent. So this is the tangent v plus c, and that completes problem number 44. Let's go ahead and do another problem. Problem number 84. Now I'm just like randomly picking some problems. You know, so on your test you could have different things. You know, you could have things that involve logarithms or e to the x. And so once again I'm just picking a sampling of the problems. Problem number 84 gives us u prime, and it gives us this function here. It's a pretty scary function, but it also gives us an initial value. So it might say solve the initial value problem. U of 1 is 0, x is greater than 0. For some reason, because, you know, if x is 0, it's going to blow it up, and maybe we don't care about negative numbers in this problem. So what I want to do on this is I want to take the antiderivative. Before I take the antiderivative, let's try to clean this guy up with some algebra. I'm going to split the fraction, and when I split the fraction, what do I end up getting? I end up getting this. X e to the 2x all over x e to the x plus 4 e to the x all over x e to the x. Now what happens on the right hand side is those e to the x's cancel, so we're pretty happy about that. But what happens here on the left term is those x's cancel. You have e to the 2x over e to the x. Now you might be a little confused, like, how do I take care of that? Well, remember when you have like an x to the 7 over x to the 4. What did you do to simplify that? You went ahead and you subtracted 7 minus 4, because there's really 7 x's on the top and 4 x's on the bottom. So this is really x to the 7 minus 4, which is x cubed. Okay, we'll put this in a cloud because this is our past here. Well, that's what we're going to do here. We're going to go e raised to the, and then we'll go 2x minus x. So 2x minus x is just an x. And then this right here is 4 over x. So take out your antiderivative gun and get ready to fire away. Now, we could have used the integral sign and all that stuff, but I had a u prime, and so this is good enough. What is the antiderivative of e to the x? It is e to the x. And the antiderivative of 4 times 1 over x is going to be 4 ln absolute value of x. Then we have a plus c. Okay, now we're going to go ahead and use this initial condition to plug that into this function to figure out what c is. This says x is 1 and u is 0. So I have 0 equals e to the 1 plus 4 ln absolute value of 1 plus c. Now, the ln of 1 happens to be 0. And this e to the 1 is e, so it looks like we'll subtract that, and we'll have c equals negative e. So we're going to rewrite this function, u of x equals e to the x plus 4 ln absolute value x minus e. And there is our answer. Sometimes when you have a condition here, you know, and maybe this is the velocity, you put the condition here sort of to remind people that, hey, only plug in positive numbers. And if really you have that condition, you really don't need the absolute value around the logarithm there. Oh well, so there's the answer to problem number 84. Let's do a few more problems here. Problem number 109. There is a rocket. And what's happening with this rocket It's got an initial velocity of 120 meters per second, and there's a platform that it is launched from, which is 125 meters above the ground. Now, the acceleration when you're working with meters and seconds is negative 9.8 meters per second squared, but we didn't write the units there. It asks us to find the velocity and the position functions and the time and position of the highest point. So that's what we're going to do. Now, before we find the highest point, we are going to find the velocity. So how do I find the velocity given the acceleration? I take the antiderivative. So this gives me negative 9.8. The letter is t now. T plus a constant. Now, what I'm going to do, this tells me initial velocity. So what really that tells me is that v, velocity at time 0, is 120. Okay, and we're shooting that thing up, so that's a positive. V of 0 is 120, up is positive. And let's put that in here. So this says v is 120 when t is 0. So we'll put that right here into this one. So 120 equals negative 9.8 times 0, so that's 0 plus c. So c equals 120. Our velocity function is negative 9.8 t plus 120. So I'll box that because they were looking for that. We also have to find s, the position. So to find s, the position, we did a problem like this on the bug on this review, but this is good. The redundancy is good for studying this. I'm going to go ahead and take the antiderivative. This is going to be t squared over 2, so it's really going to be negative 9.8 divided by 2, which I think is negative 4.9 t squared, and then plus 120t, and then we have plus a constant, c, which is different from that c there. Now, it says the platform is 125 meters above the ground. Really what they're doing is they're giving you an initial condition of s of 0, that's the height at time 0, is 125 meters. We are going to say that that's t is 0 and s is 125. We're going to plug that in there to find out what c is. So 125 equals 0 plus 0 plus c. So c is going to be 125, and your position function is really going to be this guy right here, but I'm rewriting it with my known c, negative 4.9 t squared plus 120 t plus 125. Now, some books will write out formulas for these, and they'll have this part right here, and they'll say this is v sub naught or v naught, and this is s naught. But I feel like maybe it's best for us to do this until you feel comfortable with that. Because, if I just said, oh, here's the formula that it goes into, then you're really not seeing the calculus anymore. So the other question it asks is find the time and position of the highest point. Well, you're going to be at the highest point when v, okay, so this is the next part, and I'll do it in this little corner here, when v is 0, when the velocity is 0, that's when it's going from going up to going down, that's when it turns around. So I have negative 9.8 t plus 120 equals 0. So this is 9.8 t equals 120, switching things around a little. T is 120 over 9.8. So 120 divided by 9.8 gives me about 12.24. So t is approximately 12.24 seconds. So they say, find the time of the highest point, which after 12 seconds after launching that rocket. And then how do you find the position? You put that 12.24 into the position function. So here is the position function here. And we're going to put 12.24 in there. And when you do that, I want to get to other problems. All you're doing is plugging that into your calculator. You'll get something, and I'll round 859.69, and it's a position, so meters. And so that is the rocket problem. So now we're going to move on to chapter 5, and in every time I do a problem, you could be pausing the video and seeing if you can do this problem on your own. So here's 5.1. This is the part that some people might not like, where you're asked to do a Riemann sum. Okay, approximate the displacement. So here's a velocity. It could have just said y equals x squared over 2 plus 4. Find the area. In any case, they're all kind of the same. This n tells you how many rectangles. And there's your time interval from 0 to 12. Approximate the displacement by Left Riemann Sum. Okay, so we're not actually going to do the antiderivative. We are going to try to see how to do this problem. And then it says illustrate. So what am I going to do? I'm actually going to illustrate this, start illustrating it, so it can help us figure out where the rectangles are. I'm going to draw this. So here is t, here is the velocity, and I'm going to divide this up into 2, 4, 6, 8, 10, 12. Now why did I do that? Because if you divide 12 by 6, because it's 0 to 12, you're going to have these subpartitions, and so this divides it into 6 subpartitions of 12, or 6 partitions. Why am I saying subpartitions? So there's 1, 2, 3, 4, 5, 6. That's where I'm going to draw my rectangles. Now, if you plot some points on this, like if you say t is 0, I'm going to have to scale the v-axis different than the t-axis, or it's not going to fit on the paper. So let's just say 4 is right there, and this is not going to be perfect, by the way. And then if I go, actually 4 is this one right here. So if t is 0, we have 4. Where is my whiteout? So I don't want to have that dot right there. What is happening here? Okay. So then if I put 2 into that function, I get 2 squared, which is 4. 4 divided by 2 is 2. 2 plus 4 is 6. So I end up getting 6 for that one. And I put 4 in, I end up getting 16 divided by 2, which is 8. 8 plus 4 is 12. So I end up getting 12 for this one. And what I'm really graphing is I'm graphing a parabola, but I'm plotting some points, and this is really going to help me figure out the area of some rectangles. I put 6 in there, I get 36 divided by 2, 36, 18, and then 19, 20, 22. So let's just say 22 is like right here. And once again, this is not going to be perfect on the v-axis, but I need to fit this. And then I have 64, 8 in there is 64 divided by 2 is 32. 32 plus 4 is 36. So let's put 36 right here. And we'll put that right there. And if we put 10 in there, we get 154. So I'll just put the 54 here. Once again, it's not going to be, perfect scaling on the v-axis. And then I put 12 in there, I end up getting 144 divided by 2 plus 4, 76. So let's just say 76 is right up here. Okay, and so this is like a parabola. Let's see if I can hit all those points. Okay, and we want to divide this up into 6 of these regions here. So we used fancy words like delta x, or it was dx. I think it was delta x. It happens to be the base of each rectangle. And those are some rectangles there. And look, there's going to be 1, 2, 3, 4, 5, 6, and that's what we want. We'll see if the camera's still running. It was making some funny clicking noises. I don't think it likes Riemann sums. And some of you are like, yeah, I know what it means. It's asking for left Riemann sum. So when I'm looking at this, it's going to be a rectangle. I'm going to take the height to be from the left side. So look at this I have. That's going to be the height of the first rectangle. And I didn't draw that super great. And then here's the next rectangle. And we get the height from the left endpoint in each interval. So I'm going to draw 6 rectangles. Oh boy, when I made, I don't know. Okay, well, we'll just, it looks like I missed the dots. So like I said, it's not going to be perfect on this. So we have that right there. Okay, so I have to figure out the area of these 6 rectangles, and I will add them all up. But all these rectangles have the base of 2. So when I'm going to find the left Riemann sum, I'm going to go L6 was the notation that I was using. So the area of that, and I know that looks a little weird, it has a height of 4 and a base of 2. It's going to be 2 times 4. 2 times 4. And the next one's going to be 2 times, and then this one has a height of 6. So plus 6. And 2 times, this is 2 times 12. And so the heights I figured out every time I plugged these guys into this function. That's how I got the height. So I have 12 plus 22 plus 36 plus, and we stop at 54. Okay, because I know that's not perfect. This has a height of 54. We don't want to go all the way up to 76 because we did not draw the altitude of any rectangle at 76. So what I do is I add those up in my calculator, multiply by 2, and I end up getting 268 feet. That happens to be the net area, or an approximation of the net area under the curve. But the area, you know, you're saying, well, I thought area was feet squared. Well, it's the area of those rectangles, but when they ask for the displacement is represented by the area, and so here's an approximation right there. So, you know, make sure you know how to do left Riemann sums. If you went ahead and did a right Riemann sum on this, and I don't have time to do this because I have a lot of other problems I want to do, I ended up getting 412 feet. So you can verify that. Of course it's going to be more because now the rectangles are going to be hanging outside. It's going to be an overestimate when you do right. When you do left, this is an underestimate of the area under the curve from 0 to 12. And if you do the midpoint ones, then you're actually taking 1, 3, 5, 7, 9, 11 and plug them into the function and drawing the rectangles from the midpoint. So you could look back on some of those lectures and see if you forgot about that. And what I'm getting for midpoint is 334 feet for an approximate of the displacement. So that is the Riemann sums. You'll get a few of those on your exam. Let's go ahead and do a few other things in 5.1. I know it seems like we are going a little slow, but some of the earlier sections had lengthier problems. Okay, 5.1. We also were introduced to sigma notation. We didn't use it fully. You know, it's almost like we just like, here it is, we're going to use it in future calculus classes. So I'm going to use sigma notation to illustrate this. And what I'm going to do is I have 4 terms there, so I'm going to say I'm going to just pick a letter, n equals 1 to 4. And I have to try to describe this. Well, if I just put an n there, then it says 1 plus 2 plus 3 plus 4. I really want to start at 10, so I'm going to add a 9 to it. And so when I put 1 into that formula, I get 10. I put 2 in there, I get 11. And then, 3 and 4 is going to give me 13. So that's what they want you to know how to do. Over here is just to make sure you know this notation. So when it comes up in the next calculus class, you'll know what to do. You're going to put 1 into that formula. So this is going to give me 1 squared minus 2 times 1. Then I'm going to put 2 into that formula, which is 2 squared minus 2 times 2. I'm going to put 3 into that formula, 3 squared minus 2 times 3. And then I'm going to put 4 into that formula, which is 4 squared minus 2 times 4. So all of this is we're adding things up. Now, if we had more time, I would have probably showed you how to add up n rectangles under a curve and then actually throw a limit as n goes to infinity. That's kind of neat to see, but it's not going to help us too much with the other stuff we have to do. It's great, and I'm sad to skip it, but we have to skip some things in here. So this is 1 minus 2, so this is negative 1, this is 4 minus 4, this is 0, this is 9 minus 6, which is 3, and then this is 16 minus 8, which is 8. 9, 10, 11. 11 minus 1 is 10. That is the sum that they ask us to evaluate. Let's go ahead and jump into 5.2. Do some things from 5.2 that are kind of interesting. I don't know if my pen is running out of ink. Oh well, we'll just continue. They want us to evaluate these definite integrals. The definite integrals, we could say they originally mean the net area. And so how am I going to find the net area? Well, let's take a look at some of these things. This one has a little arrow and it says the area of this guy right here is 7. Do I know how to find the area of this rectangle here? And yes, I do. It's going to be 3 times 2. So this guy has area of 6. And then this triangle here is really, look, it looks like 2 for the base and 2 for the height. So that's 2 times 2 is 4, but then you have to chop it in half. So that's actually going to be 2. Now, I'll put a 7 here, just to make it consistent. And when they say integrate from 0, x equals 0 to x equals 9, I am getting a net area, which means that these areas, are going to count as negative. And this area is going to count as positive. So basically, it looks like I have 8 with a negative. So negative 8 plus 7, this gives me negative 1. Okay, and this is not in the context of velocity, so we're just going to say negative 1 without any units. Now, but this would be the displacement, and this would be the total distance traveled if you were doing a velocity problem. From 0 to 9, so the same interval, and we are integrating the absolute value, which means instead of doing the net area, we're going to do the total area, which looks like if you add those 3 numbers, it looks like that's going to give you 15. Okay, what is the net area from 2 to 5? From 2 to 5. Okay, so wow, I have to divide this even more. And so this gives me an area of 2. I know I've kind of ruined my picture here. I'm going to circle that in red. It looks like on this one here, I'm going to change that to 4. Okay, so I'm going from 2 to 5. So going from 2 to 5, all of that is under the x-axis, so it's going to be a 2 and a 2, so that's going to be negative 4. Okay, the net area from 5 to 2. So it's like the last problem, but I've switched around the limits of integration. And what does that do to your answer then? It actually puts a negative in front of it, and you put a negative in front of negative 4, you get a positive 4. So there's properties of integrals that are good to know. What happens if I integrate from 2 to 2? well, I'm really not getting any area. I'm not moving along the x-axis, and that's going to give me 0. And the last one, maybe it's best to look at problem 3. We integrated from 2 to 5 of a function. Now we're integrating from 2 to 5 of that function times 3. What it's going to do is it's going to take this number and multiply it by 3. One thing that you could say is you can take that 3 outside the integral sign. And so really this is 3 times negative 4, which is negative 12. And so that's how you do some of those problems. Let's go ahead and do another problem that involves the integrals, the definite integrals. Okay, so look at this one right here. If, and how are we doing in terms of, yeah, it looks pretty clear. The integral from 1 to 2 of a function is 10, and the integral from 1 to 2 of another function g is 8. Then find the integral from 2 to 1 of this mess here. So the first thing I'm going to realize is this says from 2 to 1, and these guys say from 1 to 2, so I'm going to go ahead and write this as negative integral 1 to 2, 1/5 f of x minus g of x dx. So now what I can do is I can break this integral up into 2 integrals. So this is really negative 1 to 2, 1/5 f of x dx. And then we have minus integral 1 to 2 g of x dx. And then I can pull this 1/5 out and at the same time distribute that negative. So I end up getting negative 1/5 times the integral of f of x dx. And then 2 negatives make a positive, plus the integral of g of x dx. Okay, so this equals negative 1/5 times the integral of f. We have that up there, that's 10. And then we have plus, we have 8 here. So this gives us negative 2 plus 8. The answer is 6. So it's kind of neat that you take a sum or a difference, you know, in the integrand, you can break it up. And if you have a constant in front of one of the functions, you can take the constant out in front of the integral sign. If you make it all the way to linear algebra, you're going to find out that what integration is, and also differentiation, it's something called a linear transformation from one vector space to another vector space. Now that's completely in the clouds at this moment. But when you hit linear algebra, you're going to look back at calculus and go, wow, that is kind of neat. We didn't even know all that stuff. So let's go ahead and do a few more problems. 5.3. 5.3 was the fundamental theorem of calculus. And so let us see if we can take the antiderivative of that. Maybe a good thing to do is to break that up. Break up the fraction. So this is the integral from 4 to 9. This is 2 over root t plus root t over root t dt. Okay, so this is the integral from 4 to 9. I'm going to rewrite this so I can integrate it. This is going to be t. On the bottom, I have t to 1/2. I cross the line, change the sign, so it's going to be t to the negative 1/2. Over here, this is a lot easier. I have just a 1. This is dt. So now what I'm going to do is I'm going to take out my antiderivative gun and shoot each of these with my antiderivative gun. I have 2. T, I add 1 to that, so this is going to be 1/2. And the 1/2's on the bottom. When I have a 1/2 on the bottom, it's really going to put a 2 right there. Plus t. And this is going to get evaluated from 4 to 9. So I have 4 root t plus t, which is going to get evaluated from 4 to 9. So the fundamental theorem of calculus, and I believe our book called it part 2, which really kind of should be called part 1, says to actually compute this, you take the antiderivative and then you plug 9 in and then subtract plugging 4 in. So let's plug the 9 in. We end up getting 4 root 9 plus 9. And then we subtract, putting 4 in there. So 4 root 4 plus 4. So what do I have here? I have 4 times 3, which is 12. 12 plus 9. This is minus 4 times 2 is 8. And then we have minus 4. So basically we have a 12 and a minus 12. So our final answer is going to be 9. Now what did we find? We found a net area if you're interested in that, but you don't really have to draw any pictures. You're done with this problem. Let's go ahead and do another even problem from 5.3. It's this one right here. Oh, everybody's favorite, the cosecant squared. So these are ones that they're good to have memorized. The cosecant squared has an antiderivative of what? Well, has the antiderivative of negative cotangent theta. Okay, and this gets evaluated from pi fourths to pi halves. We'll go ahead and plug in, so this is the function here, negative cotangent theta, so I'm going to go negative cotangent pi over 2. Here's the fundamental theorem of calculus minus negative cotangent of pi over 4. Now if you're a purist and you don't want to just like try to see what your calculator says on this, if you remember the cotangent graph, it has many, infinitely many vertical asymptotes, and this vertical asymptote, I believe, is at x equals pi, and it also has another one here at x equals 0. And the graph goes like this, and it hits the halfway point between those vertical walls, and that halfway point is pi over 2, which means pi over 4 is right here. And if you remember anything about the cotangent, it's really the cotangent is 1 over the tangent of 45 degrees, so that's going to have a height of 1. So this is all going to help us. So the cotangent of pi halves, the y value right there is 0. So this is going to be negative 0 minus negative. Okay, the cotangent of 45 degrees, or pi over 4, is 1. So reading through all those negative signs, you end up getting a negative, negative 1, or we have just a 1 for the answer. And so that is how you complete problem number 54. Let's go do some other problems. I think on Fundamental Theorem of Calculus Part 1, I assigned the evens and the odds, so I just had to make up some problems here. So this is like saying we have the antiderivative gun, and then we have the derivative gun right outside. Now, the Fundamental Theorem of Calculus Part 1 says there has to be a constant down there and another letter up here, and your book's been calling this the dummy variable, the one that's in here. And what's going to happen is you're just going to write this function again, not in terms of x's, but in terms of p's. It's just saying that the derivative of the antiderivative is the same thing. So this is p e to the p cubed power. No plus c or anything, because if there was a plus c from this, you're taking the derivative of that. So that is what it is. Okay, so that was one problem. Another one that I just made up was this. For Fundamental Theorem of Calculus Part 1 to work, the variable has to be on the top part of the integral sign. So I'm going to go ahead and switch them and put a negative, which I'll take out in front of the derivative gun. And so this is going to become 2 on the bottom and x squared on the top. This guy right here is t cubed plus t dt. Okay, So now, what I'm going to do is I'm going to go ahead and see if there was just an x there, I'd write the answer as square root, x cubed plus x. But there's an x squared there, so I'm going to replace the t's with x squareds, and I'm going to get negative square root. So if I have x squared cubed, that's going to give me x to the 6th plus x squared. Now because I have a function that looks like this, I have to do the chain rule, and what the chain rule would say is take the derivative of that inside part. So the derivative of this part right here, which happens to be 2x. Okay, so this is the part that's being plugged in there, and so that's the part you have to do the derivative of. And so our final answer is negative 2x. I'll put that out on the left side, and then we have x to the 6th plus x squared. I know I can factor out something, but I'll just kind of keep it like this. So there is the answer. Let's go ahead and do some things in 5.4. So in 5.4, they give problems. This is where we learned about the symmetry. Use symmetry. Now, if you put a negative x in here, you're going to get like a mess. You're going to get something that's neither even nor odd. But what really we can do, and we're integrating from opposites. So this is the only time the symmetry is really going to help us. Is we're going to break, so this is what we'll do. We'll break up this integral, so it says integral of x cubed dx plus the integral of x to the 4th dx. So we can see that this guy has origin symmetry. It's also called an odd function. And this guy has y-axis symmetry, which is called even function. Now when you integrate from a negative number to its opposite of an odd function, you can always think about this graph here or think about the sign. The net area will always be 0. And if you integrate from a negative number to its opposite over an even function, the quick way of doing this is to say it's really 2 times the integral from 0 to 2 of your problem. So that's what this equals, and that equals that. So let's continue. This is going to be 2, and we have x to the 5th over 5. This gets evaluated from 0 to 2. See, it's easier to evaluate something at 0 than it is at negative 2, especially when the function looks crazier. So I have 2/5. I'll put that out front, and then I'll put 2 in here. So this will give me a 32. I'm just putting 2 into x to the 5th, the 5 I pulled out, and then 0 is that right there. So 32 times 2, I believe that is 64. 64 over 5, and that completes our symmetry problem. So the symmetry problems are shortcuts for doing integration. And let me see if I can find the other piece of paper. Here it is, the average value of a function. So here it is, average value of a function. See how we're doing with time? Pretty good. Find the average value of a function f on 2 to 4. So draw a graph of f and indicate the average value. Find all points at which f equals its average value on 2 to the 4. This is the mean value theorem. So we kind of already did mean value theorem, but we'll go through this on this problem. So what am I going to do? It says find the average value of the function. Well, the average value had notation which you can use or you don't have to use. It looks like that. And what it happens to be is 1 over the time interval, so we can say 4 minus 2. The integral from 2 to 4 of the function. I didn't even draw what the function was. Nice. So my function, f, sure hope I'll pick a good function here. It's going to be 1/4 x squared. Okay, so there it is. That's part of the problem. Okay, if that wasn't there, we'd be in trouble. So 1/4 x squared. Let's put that right here. 1/4 x squared dx. Okay, so what do we have here? This is really, look, right there, there's the displacement if f was a velocity function. And then here's the time. So we're really just doing displacement over time. So we have 1/2. The integral of this happens to be x cubed over 3. So we're going to go 3 times 4, which is 12. And this gets evaluated from 2 to 4. Now, for some crazy reason, I'm going to keep the 1/2 out front, but you don't have to. You can actually pull the 1/12 out front if you'd like. But for some crazy reason, I want to do it this way. So 1/2. Then I put 4 in for x, so I'm doing the fundamental theorem of calculus, and I end up getting a 4 cubed, which is 64 over 12, minus, and I put 2 in there, I get 8 over 12. Okay, so, and once again, this is just a matter of style, me keeping that out there, because I wanted to show you something. Looks like I can reduce the 64 over 12. 4 goes into 64 16 times, 4 goes into 12 3 times, and then we have, this is going to become, 4 goes into that is 2/3. So I have 1/2 times 14 over 3. So 14 over 3 actually is the net area of that function from 2 to 4. And since it's all positive, it actually is the area under that curve between the curve and the x-axis. And then when I multiply it by 1/2, I end up getting 14. Well, I end up getting 14 over 6, which is 7 over 3. Or, if you like, you could say 2 1/3. So there's the average value of the function. Draw a graph of f and indicate the average value. Let's do that right. Let's do it here. Why not? Do it right here. Here's x, here's y. We are interested in this graph. We know that the graph touches 0, 0, but we know at 2, we put 2 into this function, we end up getting 1. And then we put 4 into this function. It's a parabola. We put 4 into the function, we get 16 over 4, which is 4. You know, grid paper might be a little better for this. So we go like this, like that. And we're really interested, lots of times with functions, we're interested in the area between 2 and 4. In this problem, they were interested in the average height starting from here. So if you took all these points and took their average height, the average height is 2 1/3. So how am I going to illustrate that? Well, 2 1/3 is right here. This is 1, 2, 3, 4. This guy is 2 1/3. And this is what I'm going to do. I'm going to draw a line right at 2 1/3. And we're going to say that the area of this green rectangle equals the area under the curve from 2 to 4. But basically we're saying that, what is this, the average velocity equals the instantaneous velocity. That's kind of what we're saying here. the average velocity being the 14/3, and the area of that happens to be 14/3 as well. So let's go ahead and do the last part. If this was A and we just did B, let's go do C. So here's A, here is B, and C. So what does C say? It says find all points at which f equals its average value on 2 to 4. So its average value was 2 1/3 or 7/3. So we want to find, here's f, all the points, and we said times when we did the bug problems, where this equals its average value. So I'm gonna go like this, 7/3. So let's solve. We have x squared equals, this looks like 28/3. X equals plus or minus root 28/3. Well, which one happens to be in our interval from 2 to 4? It wouldn't be the negative. We can simplify this root 28/3. So x equals 2 root 7 over root 3. So there it is. So the question says, find all points at which f equals its average value on 2 to 4. So there it is. Let's box it. Now here's the deal. There could be more than one time if there's some wiggles on this interval with this graph. There could be 5 times where the instantaneous velocity equals the average velocity. If you put the answer on your calculator, you get approximately 3.055. And 3.055 is right here. 3.055. And what happens when you go up? Look, boom, right there. It hits right there. That is where the top of the green rectangle meets the curve. So geometrically, this is pretty cool. So we're done with this problem. Let's go ahead and do some U substitution. So here's problem number 34. U substitution. What are we going to do for this problem here? Looks pretty nasty. So you have to select a u, and sometimes that's the hard part. You might, let's say u equals 8x plus 6, but I'm going to go ahead and let the u equal the bottom of the fraction. 2x squared plus 3x. du is 4x plus 3 dx. So we look back at our problem and we go, oh, look at this. I have an 8x plus 6, and this says 4x plus 3. So what I'm going to do is I'm going to factor a 2 out of the top. I'll put it out here. And I'll have a 4x plus 3 dx on the top. And on the bottom I have what I set my u equal to. Okay, so look at this right here. I don't know which color I used when I did use it. It doesn't really matter now, does it? So this guy right here equals that. And here's my u, which equals this. So look at, everything's gonna kind of turn into u's here. I have a du on the top, and on the bottom I have a u. Now, if that makes you nervous, you can write it as, okay, I got to write some equal signs here. Integral 1 over u du. Okay, so we go over here and we can integrate that. This is going to be 2 times the ln, the absolute value u, plus c. And I'm going to replace my u with this 2x squared plus 3x. So this is going to be 2 times the ln 2x squared plus 3x plus c. And that completes problem number 34. Let's go ahead and do another U substitution. Oh, I think I was showing you, like, during lecture that this one can be eyeballed. Sometimes when I see something like this, so I go like this, I have a 2x squared plus 3x on the bottom, and that's what I would let my u equal. And when I take the derivative in my head, I get a 4x plus 3, which kind of we did there. And then I would look up there and I would know, oh, well, this really is a 4x plus 3 times 2. So it looks like I'm doing the same thing. 4x plus 3 times 2. And I know that that part up there will disappear because I'm doing the reverse chain rule. And then I'll say, well, how do I take the derivative, the antiderivative of 1 over something? It's going to be ln absolute value of that something. And then I have plus c. So look at that. And you're like, wow, that's a lot less work. It is, but you know, don't eyeball these things if you feel like that's making you nervous. Go ahead and do the U substitution. And there are some problems where I will actually write out the U's because it will be a little more complicated than just this. Let's go do the next problem. The next problem here is 78 U substitution. So what should I let U equal? Well, I'm going to let U equal x minus 2. du equals 1 dx. So I have this guy set up right here, and I have the U substitution right here. But there's a problem. There's an extra x on the top. So what am I going to do with this extra x? Well, I'm going to go ahead and rewrite this. I can solve for x here, and I see that x equals u plus 2. So I'll circle that in blue. So my integral now becomes u plus 2 over u du. This can get broken apart. Split the fraction, you get 1 plus 2 over u du. Integral of 1 is u. Integral of 2 over u is 2 ln absolute value u. We have a plus c. And then, we'll bring it up here. This u becomes x minus 2. And then we have plus 2 ln absolute value of x minus 2 plus c. So lots of times people will go, okay, there's my answer. Now here's something that's going to trouble some of you. Okay? I'm going to rearrange the terms of this answer. I'm going to put the minus 2 here. No, let me go plus c minus 2. Well, what is c minus 2? Isn't c minus 2 just another constant? I'll call it red c. And so when you're doing problems, sometimes you may see, no pun intended, the answer like that right there. Probably on the next test, if this happens, I'll let this slide. But really, this is more simplified. So that is problem number 78, with a little surprise at the end. I would not be eyeballing this one. Believe it or not, I couldn't eyeball this one. because there was this extra part where I did in blue. Let's go ahead and do this problem right here. Now, of course, we could eyeball these things. I'm going to go ahead and write out the u's. If you want to follow the other way, you can. I do want to finish this review. I don't want the review to be like 4.5 hours. So I'm going to let u equal what? Well, maybe theta over 8. So du is going to equal, so this says 1/8 theta, so it's going to be 1/8, taking the derivative, and then a d theta. Okay, so you could put parentheses around the argument of the cosine if that makes you feel more comfortable. So I have 8 du equals d theta. So look at this. This guy right here is going to replace that guy. And then my u, which I've been using green for this review, is going to be that right there. Now remember that I also have these values up here, which some of you might keep and then change everything back to x's when you're done, but I'm going to go ahead and change them. So these are, well, not x's, but thetas. So these are theta values. Theta equals 2 pi. Theta equals negative 2 pi. So when you put 2 pi in for this, you end up getting u is 2 pi over 8, which is pi over 4. So on the top you have pi over 4, and on the bottom you have negative pi over 4. This is the cosine of u, and then this is du times 8, and I'll put the 8 out there. Now here's the really cool part. This guy right here is an even function. So if you want, and this is optional, you can say this is really going to be 2 times integral from 0 to pi over 4. And this is going to be of cosine u du. So this is 16. The antiderivative of the cosine is the sine. And we're evaluating this from 0 to pi over 4. Okay, so this is 16. We put pi over 4 in there, and we end up getting, I'll just keep the 16 on the outside, sine of pi over 4. And then this is minus sine of 0. Pi over 4 is a 45 degrees, 45, 45, 90. So this is 16 times 1 over root 2, and then the sine of 0 is 0. This is 16 over root 2. I'm going to rationalize the denominator because it can look cleaner for my final answer. This is 16 root 2 over 2, which is 8 root 2. Now 16 over root 2, I'd probably be happy that you got there. 8 root 2 just looks a lot cleaner, and that is the answer to problem number 50. Let's go ahead and do another problem. Number 64. I believe there's only 2 more problems that I'm going to do. I'm going to do this last problem from 5.5, and then I'm going to go ahead and do a problem from 6.1 that has to do with the population. So I'm integrating from 0 to ln4 of this mess here. Wow. So what should I let u equal? Well, some of you might say let it equal e to the x, but you'll still have a mess. U over 3 plus 2u. Some say let it equal 2e to the x. But what I'm going to do is I'm going to let u equal the whole bottom of the fraction. Now, if you were going to eyeball this, you would say, oh, the derivative of the bottom is what? 2e to the x. And I would put a 2 up there and a 1/2 out front and start eyeballing this problem. I wouldn't even change those. But I'm going to go ahead and do this the textbook way. du equals 2e to the x dx. And you do notice that I have an e to the x dx. So I'm going to divide both sides by 2, and I have du over 2 equals e to the x dx, which I'll circle in orange. My U substitution is this guy right here, which I'll circle in green. And these values on the limits of integration are x values. I have to change them to u values. Now, how am I going to do that? Well, let's start off with 0. When I put 0 in for x, I end up getting 3 plus 2 e to the 0. E to the 0 is 1, so 3 plus 2 is 5. Okay, now this one we might want to write out. Put in ln 4 for x. I have 3 plus 2 e to the ln 4. Well, this right here is one of the properties of logs. I call it the popping property. That thing goes pop, and you end up just getting the argument of the log. So it looks like 2 times 4 there, which is 8 plus 3 is 11. Now some of you are like, that's why I don't change my limits of integration. You would still have to deal with this if you didn't, and you did an eyeball method or whatever you wanted to do. So look at this. We have a du over 2. I'll put the 2 on the outside. And then I have, this is u on the bottom. So 1 over u, the integral of 1 over u, I believe, is the ln absolute value u. So this is 1/2 ln the absolute value u, evaluate it from 5 to 11. So this is 1/2, and I'll just put that outside there, and I'll go ln absolute value of 11, which is 11, minus ln absolute value of 5, which is 5. This is an acceptable answer, but if some of you want to impress the girls, or the guys, whatever, we can use properties of logarithms to write it as ln 11 over 5. Wow, so that looks sweet. So both are acceptable. And that is U substitutions, which will come up in lots of technical classes. Our last problem of the review is in 6.1. And I know I didn't do like bacteria and culture and think cultures like, but we're going to do this because it's just like a population problem. It's like the population of wolves or wildcats or whatever. You have a culture of bacteria in a petri dish, has an initial population of 1,500 cells, and grows at a rate in cells per day of n prime equals 100 e to the negative 0.25 t, where t equals days. And I guess that's a period there. Okay. What is the population after 20 days? After 40 days? Find the population at any time. So here's the deal. I'm going to do part B first, and then I'll use it to do part A. Your book does these problems a little weirdly. Just ignore them unless it makes sense to you. So what am I going to do? Okay, so what am I focusing on? Here's the derivative, the rate of change of the number of bacteria. And it's changing like this. So what I want to do is I want to get n of t, which is the antiderivative of this. So that's what I'm going to do. N of t equals. Now some of you are like, wow, Joe, this is really weird. Okay, let's just rewrite this again. This is 100 e to the negative 1/4 t. So maybe off to the side, we can put this in an integral problem here. So this is the integral of 100 e to the negative 1/4 t dt. I'm going to eyeball this, and if you want to do a U substitution, let u equal negative 1/4 t. I eyeball this, and then I say, what is the derivative of that exponent? It's negative 1/4. So let's put a negative, I don't know where to put it. I'll put it right here, negative 1/4 right there. Put it right next to that dt because that's going to disappear. But I have to balance the books and put a negative 4 out front. So when I integrate this, I'll write that as negative 400 and because of that 100 times negative 4, this part is going to disappear, and the antiderivative of e to something is e to something. And then, of course, we have the plus c. So you could have done a U substitution, let u equal negative 1/4 t. You'd get the same answer. So coming back here, I know that I'm going to get negative 400 e to the negative 1/4 t, and then plus c. So what am I going to do? I have to find that c. How am I going to find the c? Well, up here they give me some information. Up there they told me that the initial population is 1500. That really means n of 0 is 1500, which means time is 0 when the number is 1500. I'm going to plug that into here, and I end up getting 1500 equals negative 400. You put t equals 0 up in that exponent, you're going to get e to the 0, which is 1, and then we have plus c. So what does c equal? Add 400 to both sides, you get 1900. So the answer to part B is writing out this function, and now I know what c is. So this is n of t equals negative 400 e to the negative 1/4 t. If you'd like, you can keep the negative 0.25 t if you'd like. And then we have plus 1900. Now part A, so now we'll go over here and do part A. Part A says, what is the population after 20 days? And t is measured in days, so what are we going to do? We're going to go ahead and go n of 20. And I'll round to the nearest whole number. So n of 20, when I plug that in, I ended up getting 1,897 cells. That is after 20 days. And it started off with 1,500. And then after 40 days, put 40 into this function for t, we end up getting 1,900 cells. And I believe I rounded it to the nearest whole number when I did that. And that completes the review, our last video for this class this semester. Study hard and have a good day.